All right, welcome to another video presentation, eager learners. We're down to 3 lessons left in an amazing kind of year in so many ways, and so we're going to go into this idea of the concept of a limit. Very important for calculus, and so we want to get you started thinking about this so that we can hand you off to the calculus people and you'll have some idea what they're talking about from the get-go. And what we're kind of looking at when it comes to the concept of a limit, it was meant to answer the paradox in math of trying to approach a door. Say you're needing to leave a room, you're 10 feet away from a door, and you get halfway, that makes you 5 feet away from the door. And then you go another halfway to it, and you go to 2.5 feet away from the door, and you keep cutting that down by a half and a half and a half. It would seem you would never reach the door, but your experience and my experience tells us, yeah, we do reach the door, we will get out of the room, and somehow the limit of that process is that we reach the door, turn the knob, walk out, and we're good to go. So it's a really powerful idea because it allows us to process things mathematically that you might otherwise just abandon. Like maybe up here, what if you're trying to get to 0, yet your function or your expression goes undefined at that value? Well, limits help us to figure out some kind of answer for that, or maybe there isn't one. So we're going to relate that to geometric series, which is this, and we just took a test over it, so it should look quite familiar to you. And you know, you look at something like this infinite series where you're just going from k equals 1 to infinity, and you're just following this pattern where you're starting at 1 and your r value is 1/2, so we can kind of list that. A1 is 1 and r is 1/2. All right, and we had formulas for this. So you recall we had the sum of all of these k terms is going to be your first term, which is 1, over 1 minus 1/2. Right, so that was 1 over 1/2, which we can simplify to 2. Somehow or other, despite the fact that you're continually adding tinier and tinier and tinier amounts onto this series, you will ultimately converge on a single number. So that's kind of amazing. So now we're going to change the notation a little bit, and we say that the limit as k approaches infinity of this particular sum is going to equal 2. All right, so you're going to see this in action with something that is going to be kind of obvious for you, and that is right here where you're trying to take the limit of this expression as x approaches 2. Now, that also means not just approaching it from numbers below it, but maybe approaching it from values above it too, in both directions. And you know that if you plug a 2 in here, yes, you'll get 6. So we can just kind of remind ourselves that while f of x equals 3x, f of 2 will actually equal 6. It's not always the case that, you know, as you approach 2, or in another setting, that the actual function evaluation will equal or be the same outcome as what you would get from a limit. We're going to see that. So here is the kind of reasoning that we're going to use. So we're going to take values that are below 2 and kind of approach it and get closer to 2. So let's just start with 1.9. If we put a 1.9 in for x and triple it, you get 5.7. All right, that's kind of close to 6. Let's get closer with our input, 1.99. And if we triple that, we're going to get 5.97. And if we get even closer to 2, oops, that's not what I want. Let's change that. Okay, hold on. Be gone, you. All right, so we'll just do 1.999, and we'll triple that, and we'll get even closer to 6, 5.997. And let's just say, we don't want to keep doing this. This gives us the idea that from the left, we're getting close to 6. So let's kind of see what happens when we approach it from the right. So let's go something really close to 2. 2.001. And we'll triple that, and we'll get 6.003. And we'll get a little further away, 2.01, and that'll be 6.03. And then 2.1 will give us 6.3. So as we approach from the left, and as we approach from the right, we are seeing these numbers converging at 2. So therefore, we're just going to say that the limit as x approaches 2 of 3x equals 6, which again is the same as plugging a 2 in here and getting the 6, which is again not always the case with limits and a function. So what I'm going to do now is pause and write out a lot of stuff that'll kind of keep you from having to sit here while I do it, and then I'll reactivate, and we'll go ahead and you can copy at your leisure. Alright, so I'm back, and you can see what I've written here. It just says as x approaches 2 from the left, the function values or the y values appear to be approaching 6. As x approaches 2 from the right, the function values or y values appear to be approaching 6. Okay, so you can pause and jot that down if you feel you need it. This is what we're talking about graphically, so we'll just put some marks here. Just can write 1, 2, 3. And we'll just make it a little smaller here. 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3. All right, 6 is about right there. All right, so if we just deal with the function as a linear, right, we'll have a point here. We'll have a point at 1, 3, roughly right here, and a point 2 and 6, which is roughly right here. It does line up as a linear, as you might expect. So let's see if I can make that fairly straight. Good enough. All right, and we're just interested in what happens as x approaches 2. So we'll just go ahead and indicate that as such. But that's sort of a functional way of looking at it. We're interested in as x approaches, goes towards 2 from this direction, and goes to this direction, where do we end up with y? And we end up at 6. Okay? So that's kind of the gist of limits. Let's just kind of play around with this with other situations. Say, take, for example, this next one up here. Come on, you. Number 2. And this is an interesting one. We're going to kind of approach this in the same way. We're going as x approaches 0. Clearly, if we were to plug a 0 in here, things would go undefined. So let's kind of approach 0 and see what happens. So we'll put in a negative 0.1. That's pretty close. And if we put that in here, it's a negative 1 over negative 1, which is 1. Okay? And then let's get a little closer to 0, so negative 0.01. And that'll give us 0.3 zeros and a 1. And if we put in a negative 0.001, then we'll get, like, I believe it's 5 zeros and a 1. So go write a little smaller, 1, 2, 3, 4, 5, and 1. There's a 1 there somewhere. And so let's go on the other side of 0, because we're really getting pretty close to 0 here. So let's just go 0.001 in the positive, and that'll give us, again, 5 zeros and a 1. And if we get a little further away, 0.01, that'll give us the same as we have over here, 0.001. And if we go to 0.1, then we'll get 0.01. Yeah, I think maybe this should have been a 0.01 here, so let's fix that. Or maybe not, let's think. That would be 0.1. No, it wouldn't. This is probably right, 0.01. So you can just see that as you go this way close to 0 and get this way close to 0 for x, that this right here is actually approaching 0. So the limit as x approaches 0 of x to the third over x is 0. Now notice, even though f of 0 is undefined, nevertheless, the limit exists. So interesting. This is our limit. If we plug a 0 in, we don't get this number. We just get undefined. So you can start seeing some of the power of this. Let's go on to example 3. So let's do the same kind of thing. Now we've got the absolute value of x over x, and we're looking at where x approaches 0. Again, this is going to go undefined if we were just to plug a 0 in. So let's see what happens. So negative 0.1, and that will give us an output of -1. And then we can put in a negative 0.01, and that's basically that over itself as a positive over negative, so that would be a -1 also, and then negative 0.001, and that'll give us a -1. So we're getting kind of close to 0. So then we'll start going above 0 to see what that does. So 0.001, and that absolute value over itself is going to be +1, and then 0.01 give us a 1, and then finally 0.1 would give us a 1. Well, from the left it looks like we're approaching -1, but from the right we're approaching a +1, and we're not seeing a limit here. It has to converge on the same number. So remember, f of 0 was undefined, so we couldn't get a value for that. And pause just a second here while I draw another graph. I don't want to put you through the torture of having me draw that, so I'll be right back. Alright, so got that looking halfway decent, and let's sort of just explore what's happening here. So we can just go ahead and sort of graph what's going on here. And if we put a 1 here, let's get that to draw, and we put a -1 here, what we're seeing is that as x is going to the right, you're going to get something that looks like this. And if we look at the other side of this, it's going to go like that. And you can see that these things are not approaching from the left and from the right. They're approaching two different numbers, right? So here the limit does not exist. This is called a jump discontinuity. And you may remember this from all the way back in August. We had 3 kinds of discontinuities, and this was one of them. So not only do we have evaluating 0 through here going undefined, that just note that the limit as x approaches 0 of this expression, absolute value of x over x, we would say that that does not exist, because left and right we are not converging on the same value like we did here in the previous example, or one of the previous examples. So this can happen. Jump discontinuities, that can create an impossibility as far as getting a limit goes. So we saw where we had a limit and the function behaved kind of similarly. We saw here where we had a limit, but f at 0 was undefined. So we had one existing, the other not. And then we had both that were not existing. So time to change paper, so stand by. All right, so now we're on page 2, and we're looking at the next example. And piecewise functions. We have not looked at those in a while either. So I've gone ahead and taken the liberty of getting this started. We'll put in some more marks here because we want to kind of examine limits in this kind of a setting. So 1, 2, 3, 4, and we'll start out with this bottom one here. If x is greater than 0, which puts you right on the y-axis, then you have a constant function. So this right here is an open circle here, and then a horizontal line or ray going to the right. And then we have this, which is linear, and that would be the same as negative x plus 1. So we'll start here, and this is less than or equal to, so we can close that off. And by the way, this will still pass the vertical line test because this is open and this is closed. And we have a slope of 1, negative 1 after that, so over 1 and up 1, over 2 and up 2. So we're looking at this. Hopefully I get that looking halfway decent. Well, not too great, but we'll live with it. Pretend that's straight. Okay, so we're supposed to evaluate what's happening here with these limits. Now this is a little bit small, but if you look really closely, this has a little extra notation on it. This is the limit as x approaches 0, and you see the little negative sign right above it? That means from the left. So make a little note to yourself that that's from the left. So we're not worried about going, to the left and to the right to try to converge. We're only coming from the left-hand side and approaching 0 from there. So as x approaches 0, you can see what f of x is doing. It is approaching 1. It'll ultimately end at 1. So then they're asking us, well, what about the limit for this function as x approaches 0? And you notice that there's a little extra tacked on here. It's a plus sign. That means from the right. All right, so our function from the right is up here at the constant part of it, and it doesn't actually, well, it approaches 2, where y equals 2. So see how they're approaching two different things from left and right? So what we can say here, this is the limit as x approaches 0, and that would be from both left and right. Well, you're approaching 1 from the left and 2 from the right. That's two different numbers, so this is a does not exist. However, f of 0 does exist, all right? All we have to do is find 0 and read up, and that's going to be 1. So kind of an interesting thing when you've got a piecewise and things are happening two different ways from the left, one way from the left, one way from the right at a certain value. Okay? So let's scoot over to the next situation, and this may help to maybe nail down some things. So up here, the math language can get a little confusing, but if f of x becomes arbitrarily close to a unique number L as x approaches a from either side, then the limit of f of x as x approaches a is L. All right, this is written as the limit of f of x as x approaches a equals L. And you can see that in this particular drawing right here. Basically, you can see right off the bat that if you are looking at what this function is doing at a and just go from a up and over, then the output here is L. It's also true that if you are approaching this value from either side, as x approaches a from the left, as x approaches a from the right, it is going to converge on L. So we can also say that the limit as x approaches a is going to also be L. Now I want you to contrast that to this. Okay, in case 2 it says the limit is not the value of f of a. What we have here, it's really kind of hard to see it on this copy, but right at that point where we go up to the curve and go over, this is actually a hole. And that's just a removable discontinuity. We'll talk about that in a minute. So at this a value, there's actually a point that is off of this particular curve. This is not continuous. The curve has a break in it. And at that particular value where x equals a, the curve doesn't have a value, but there is a value where x equals a. So here's the neat thing about it. As we go from left to right, we can say that the limit as x approaches a of this particular function is going to be L. However, if we want to just evaluate that function at a, then it's going to give us up to the point and over, and it'll be below the curve, and that's going to be R. Interesting. So the limit is one thing based on approaching, and it doesn't matter if there's a point there or just a missing point, it's still approaching that spot, and we can read that as L. However, if we wanted a place to stand, in this function, we would fall through this hole, but we would be able to stand here. So the function does exist at a, it just gives us an output of R. However, the limit of this function at a is going to be L. So that's an important thing. And in this case, the limit is not the value of f of a. All right, I'm going to pause and write a few more things and try to spare you having to sit through that. So stand by. Okay, so magically you've got some more writing here, and it goes back to this removable discontinuity or hole, and that's just a break in of one point, like a missing point in an otherwise continuous curve. And what we saw here was that the existence or non-existence of f of x at x equals a has no bearing on the existence of the limit of f of x as x approaches a. So we could have just left this point off and have this function be discontinuous at a. And we would have said that, f of a does not exist if this point were not here and the hole was. But the limit does exist, because it's almost like thinking about this as a manhole cover. We can't stand on it, but we can identify its position. So removable discontinuity, jump discontinuity, all have implications for limits. So it's time to go to another page, so stand by while we do that. Alright, so we want to look at just a few more things, look at where limits fail to exist, and these are some pretty classic examples. So we'll look at the first one where we have unbounded behavior, and the example that we're seeing here is the graph of f of x equals x squared. So basically what we're seeing here is that the limit of f of x, in this case 1 over x squared, as x approaches infinity, or I'm sorry, as x approaches 0, is going to be does not exist, because what's happening is that it's going on to infinity. So that's another way to describe it. But keep in mind that infinity is not a number. It's just a behavior description. Where is it heading towards? But it is not a number. So keep in mind that infinity is not a number. All right, so we can't actually say that it's going to approach this or that. It's just going on unbounded. So a better description, well, this is a good description, but the answer for this is basically does not exist. And keep in mind also that f of a is undefined. So what can we say here? Just for your notes, just say that however, infinity is descriptive of the function around x equals a. Make that a little better. Of the function around x equals a. All right, so approaches infinity from the left and from the right. That is a great descriptive, but it actually does not exist. All right, here's another interesting one. This is a function, but you can see it's got oscillating behavior. It's oscillating between -1 and 1. So basically, f at 0, because we're looking at what's happening around 0, is undefined. The limit as x approaches 0 of this function, we'll just say pi over x, does not exist. We'll just do the dne thing. So when you see the oscillating behavior, you can't get a limit where it's oscillating on either side of your target, which would be, in this case, 0. So f of x is oscillating. Between -1 and 1 as x approaches 0. All right, so now we've got another thing. This is your greatest integer or step function. And if we look at this, let's just say we want to find the limit of this absolute value of this greatest integer function as x approaches 2. This is going to be that it does not exist. And we can see that because we'll just examine, for the first case, the limit of this greatest integer function as x approaches 2, and let's just say from the right. All right, so as x approaches 2 from the right, you're up here at 2. This is up here. So you're going this way, and you're approaching 2. So this would be 2. However, if we look at the limit of this greatest integer function as x approaches 2 from the left, all right, and that would be here. And so basically, we're looking at an output of 1. So you can see that these are two different things, two different values. And that's why this limit overall from both sides doesn't exist. That's much like what we had in example 3. Okay, so the very last thing is going to be an infinite discontinuity, and I just want to spend a moment on that. So I want to draw it, so stand by while I do that. Alright, so here we are, and I just put a little quick set of axes here. And we're just going to look at, we'll call this example 4, just this is the function f of x equals 1 over x, which you remember is just the parent for your reciprocal function. So it looks kind of like this. And we can look at the limit as x approaches 0 of 1 over x. And this clearly does not exist. And the reason why is because if we approach it from the right, we're seeing that this is just going to go to infinity. So let's just say that the limit as x approaches 0 from the right of 1 over x, and this does not exist, but we'll use the descriptive infinity. And so that's sort of the one case. The second case here is the limit as x approaches 0 from the left, and you can see that's just going to drop down. So of 1 over x will be negative infinity. Even the descriptors are different. So overall we just would say this does not exist. And this is our last kind of discontinuity. This is going to be an infinite discontinuity. All right, and we can also say that f of 0 is undefined. All right, so that's your intro to limits. It's kind of a crude way of looking at it. Eventually we'll get limits done algebraically, but I've taken up enough of your time, so I'm going to go ahead and cut off for now, and we'll see you next time. 1 down, 2 to go.